So good morning. Today we are going to understand why we require this creation and annihilation operators. Okay. So basically we have seen this creation and annihilation operator in many research papers and many books also that they are using this annihilation creation operator. We said that we have seen that there is written some kind of second quantization operators and many things. Okay, those are associated with this annihilation creation operator only. Basically, those second quantization operators are written in the form of this annihilation and creation operator. So question is that why we are using these annihilation and creation operators. Okay, and if we are using it means that it is more uh, useful and more very useful for us. That's why we are using this. It simply simplifies our mathematical complications and many things maybe. So due to that we are using this annihilation creation operator. So today our interest is to understand why we are using this annihilation and creation operator. Okay, so before that let's discuss that. Say we have a many particle system. Okay, so this many particle system among, so in this many particle system this particles may be either fermions or bosons. Okay, so now in order to describe those many particle systems, say it will be fermions, so we need a wave function. Okay, and that wave function will describe this total many particle system. So we are considering fermionic system wave function. Okay, now first of all let's understand how this wave function has been written. So first of all consider in this phi mu 1 1. Okay, this phi mu 1 1 said in that many particle system, say we are considering one particle. Okay, that particle is at particular coordinate, so that coordinate is signifies 1. Okay, and that particular particle have some state. So for that phi mu 1. Okay, so this is a single particle state eigenfunction or eigencat, whatever you can say. Okay, so there are n number of particles, so there will be n number of uh, single particle states. Okay, now basically we had written this in this single particle state in terms of this determinant. Okay, so let us consider that there are only two particles. Okay, so and this determinant is basically n cross n determinant. Okay, so we are considering only two particles, so it will be only this part only we are considering now. So when we explain this determinant, what we do, phi mu 1 1 into phi mu 2 2 minus phi mu 2 1 into phi mu 1 2. Okay, and that's by 1 by root over and 1 by root over 2 2 2. Okay, 2 factorial means 2 only. Okay, so in this way we write this particle system for two fermions. Okay, so in case if there are n number of particles, so for that we'll write this way for that we'll write this wave function in this way, and basically we will expand this, so we will get total particle wave function for harmonic system. But now let's discuss about many particle system for bosonic system, many particle system, and those particles are bosons. Okay, so now discuss that. Okay, now basically what's the difference between harmonic particle and bosonic particle? What happens is that in case of harmonic particle, okay, these harmonic particles follow Pauli exclusion principle. That means each particle have different states. No identical particles. No two particles have same will be in same states. Okay, this is basically the Pauli exclusion principle which followed a harmonic particle. And this just remember this n is that total number of particle in many particle system. Okay, and total water harmonic system. Now we are talking about bosonic system. Okay, so bosonic system, this n particle wave function will be, it takes same form but there are slight modifications. Those modifications are this say say there are only two particles. Okay, so what we do is that 5 mu 1 into 5 mu 2 2, we multiply this. That's why in case of formulae what we do is 5 mu 2 1 into 5 mu 2 2, and we just multiply this and multiply and we just do minus. Okay, but in this case we will do plus. Okay, so we will multiply this and multiply that, and that's why we will plus. So basically when we expand this determinant in case of bosonic system, when bosonic and particle system, we will not obtain any kind of minus sign. Okay, but in case of harmonic we may obtain some minus sign, we may not, we will obtain minus sign. Okay, now even we know that in case of bosonic particles, say in a particular state 5 1 there can exist two particles. Okay, but this is not the case of harmonic system, where in each state there will be only one particle, so there will be two particles. So root over n factorial, here root over n factorial into 2 factorial due to these two particles in a same state, and here only one particle, so 1 factorial multiply root over n factorial 2 factorial into 1 factorial. So here, so and here only no particles, so 0, so 0 factorial will be also 1 only. And say in 5 4, in 5 4 say there are 6 particles, so root over 2 factorial into 1 factorial into 0 factorial into 6 factorial. So in this way, we can say that this many particle system wave function for bosonic system we can write. Okay, so till now we had studied many particle system wave function for bosonic case and harmonic case. Okay, now what so happen is that if we are going to write this n particle wave function, then there are many eigenstate we have to multiply, and in this way we expand it. Okay,